Hello everybody, Hobo here, and today we are going to have a great time because now that we've established a foundation to the Fourier series in the previous videos, we will be able to isolate and find solutions to the a sub n and b sub n Fourier coefficients. So this video will primarily focus on the solution to the a sub n coefficient. So let me jog your memory. Let's remember what the Fourier series actually is. So if we have some f of x, then the Fourier series of f of x is a periodic approximation of it's an infinite sum of trigonometric functions that closely or globally approximate the f of x function listed here. And let's note something. This has to be periodic. And when we try to approximate a function that is not periodic with the sum of sine and cosines, or the infinite sum of sine and cosines, if you will, that is going to be the Fourier transform, not the Fourier series. So that's a slight digression, but we will be covering the Fourier transform in a different video. So our f of x needs to be periodic, and then if it's periodic, and just for ease, we will be working with 2 pi, so it will be periodic over 2 pi. Then the Fourier series is the infinite sum from n equals 1 to infinity of an cosine of nx plus bn times the sine of nx. And so this makes sense because it's the infinite sum of varying trigonometric functions which have different frequencies and therefore combine to produce different frequency functions, and each of these trigonometric functions with different frequencies is weighted differently, and that's produced by the an and the bn's here. So because of the differing weights, we can get different resultant functions with varying frequencies and varying amplitudes. So this is why the Fourier series is extremely useful. But so far, oh, my apologies, I forgot to list the phase shift term, which is a0. So yes, and then there's the a0 term, which is just a vertical shift. That means that if I have my function here, which I'm trying to approximate, let's say, then if I add sine and cosines over here, then that's gonna produce this resultant function, but shifted down. So I want to shift this sum up, so that's why I use my a0 term. So we've already derived the a0 term for a 2 pi periodic function, and that a0 term was equal to 1 over 2 pi, integral from 0 to 2 pi of f of x dx. And today we will try to isolate and produce a solution to the a sub n term. So let's begin. So how we begin is we multiply both sides of this equation right here by cosine of kx, where k is an arbitrary integer. So let's have f of x cosine kx. Oh, let's write smaller here. We won't have enough space at the end. So we have f of x cosine kx is equal to a0 cosine kx plus the infinite sum from n equals 1 to infinity of an cosine nx cosine kx plus the other infinite sum from n equals 1 to infinity, and we break it up into two infinite sums just for simplicity here, but you can always keep it as one sum. But n equals 1 to infinity of b sub n times sine nx times cosine kx. Now that's a mouthful, but now that we have this here, we can just erase the original Fourier series, and we have this. So now what do? This seems like a fairly complicated, gnarly equation. Well, to simplify a lot of these terms, we simply integrate on both sides, and we integrate term by term on the right-hand side, and we integrate just the entire function on the left-hand side. So then what we produce is, my apologies, the limits of the integration will be from 0 to 2 pi, since f of x, as we clarified earlier, we suppose that it is a function which has period 2 pi. So we have 0 to 2 pi, integral f of x times cosine kx, and remember k is simply an arbitrary integer, is equal to a0, our integral from 0 to 2 pi of, and we can always pull the a0 out because a0 is a constant for all we care, and so that's cosine of kx dx. Oh well, I have to add dx's here, don't I? Cosine kx dx is equal to a0 integral 0 to 2 pi of cosine kx dx plus, and now I'm going to erase this section, plus the integral, the sum of a sub n equals 1 to infinity a sub n, and then I'm going to erase this here really quick, times integral 0 to 2 pi, and then remember that term, that is just cosine of nx cosine of kx, and then we added dx for our integration here. And then when we integrate this term, then we have plus the sum from n equals 1 to infinity of b sub n. And the reason that we can pull out the b sub n and the infinite sum here is because the integral of a sum of certain terms is equal to the sum of the integral of those terms. So we can always pull the sum out of an integral. And since b sub n and a sub n are constants when we're observing a certain n, then we can pull those out as well. So now we have times integral 0 to 2 pi, and then what's this term here? That's sine nx cosine kx. So we have sine nx cosine kx, and let me squeeze a dx into there. So wonderful. Now, I promised that our equations would get less complicated, but it seems that they got more complicated. But not to worry, we still have a few steps to go, and everything will start to fall into place. So, let's observe this first integral here on the right-hand side. So that is equal to a0 times the integral from 0 to 2 pi of cosine kx dx. And let me restate this again. K is an arbitrary integer. And if you don't know what this bold-faced z means, it's simply the set of all integers. So, k is simply an integer, and the integral from 0 to 2 pi of cosine of an integer times x dx is always going to be 0. We've discussed that in a previous video. So this term we can forget about. Wonderful. And then we're left with this is equal to this plus this. And well, let's see here. What's the integral from 0 to 2 pi of cosine nx times cosine kx dx? Well, we covered this as well in a previous video. It's equal to 0 everywhere. except when n is equal to k, because then you have integral 0 to 2 pi cosine squared x dx. Oh wow, cosine squared nx if you want, nx dx, and you can evaluate this, and it evaluates to pi when n is equal to k. So that's the only instance where this integral here evaluates to a non-zero value. So then we have the infinite sum from n equals 1 to infinity of a sub n times pi for when k is equal to n. Well, if this integral evaluates to 0 everywhere except n is equal to k, then all these other terms between 1 and infinity where n is not equal to k are going to evaluate to 0, or at least the product is going to evaluate to 0. So then the only term that really does matter is when n is equal to k. So let's take not n is equal to 1, but n is equal to k, and let's just assume that n is equal to k, then we have a sub k instead of a sub n. So that's a sub k, and that's integral from 0 to 2 pi of cosine nx cosine kx dx, and we discussed this, it evaluates to pi. So then we have pi times a sub k, ak pi. And wonderful, now we're left with this last integral to evaluate. Well, the integral from 0 to 2 pi of sine nx times cosine kx dx is always equal to 0 for whatever integer values n and k hold. So then we can cross this entire infinite sum out, because the infinite sum of zeros is always going to be equal to 0. So then we have the integral from 0 to 2 pi of f of x times cosine kx dx is going to equal a sub k pi. Well, let's isolate a sub k. A sub k is equal to 1 over pi, 0 to 2 pi. This is a very hard step. F of x dx. My god, that was hard. Alright, well, now comes the... Oh, my apologies. F of x times... that was extremely hard, but I still managed to screw it up. Times cosine kx dx. And now what we can do is we can substitute, we can exchange x instead of k, and no, n instead of k, my apologies. So then we have a n is equal to 1 over pi times integral from 0 to 2 pi of f of x times cosine nx dx. So what we have effectively done is we have given the Fourier series of a certain function, a certain periodic function, certain 2 pi periodic function, f of x. We can determine the leading coefficient of the cosine function given whichever term you want to calculate in your series. So given the first term, we can always plug in n is equal to 1 and so on and so forth. So that is QED. Thank you very much.